today's video is going to be a little bit shorter than the last one, and what we're going to do is build off of what we talked about in terms of ideal chain statistics to talk about the size of a polymer, remind ourselves some things about the number of microstates that a certain polymer chain might have, and then use those to construct the free energy of an ideal polymer chain, or what we're going to call a Gaussian polymer chain. We use those words kind of interchangeably. So as an outline of what we'll talk about in this video, the first thing is I'd like to go back and just very briefly review what we call the radius of gyration. But not just that, talk about the radius of gyration as well as the mean squared end-to-end distance. And so I'm just going to write this like this now, because we know what that terminology means. After we talk about that and calculate the radius of gyration for a couple of different architectures, actually I'm only going to calculate it for one architecture and then show you what the expression would be for some other polymer architectures, just give you the results. After we do that, we're going to move into a discussion of scaling, which in my opinion is one of the most important things that we do in polymer physics and polymer physical chemistry. So in other words, sometimes our systems are so complicated that we don't necessarily know all of the details. So for example, we don't know all of the numerical prefactors that go into constructing some kind of model for how polymers behave. And so we get rid of those prefactors and we kind of extract the essential behaviors. And so the mathematics becomes much simpler in this case, and it gives us some kind of understanding of what's going on with our system. So for example, if I was to double the molecular weight, what do I expect to happen in terms of X? Okay. So we'll talk about what scaling is, and we'll also talk about what we call the fractal dimension. So not super important, but, well, I shouldn't say that. It is important, but it's not super important for what we're talking about now. But these are things that show up from time to time, and we'll use them next semester also to kind of compare and contrast the differences between these ideal polymer chains and real things that we actually that we work on. And then the very last thing that we'll do in this video is we will construct the free energy. And in this case, we will construct the Helmholtz free energy for an ideal polymer chain. And with all of that combined, then we'll be in a really good place to start building upon this to talk about things like, I don't know, the behavior of rubbers, rubbery networks, things like that. All right? Okay, so let's get into it. The first thing is with the radius of gyration, we came up with an expression. I just gave you an expression towards the end of class last time. But let's go through what it is. And so the first thing is that if we remind ourselves about this mean squared end-to-end distance, it's telling us something about the polymer chain. So for example, we calculated that this is going to be equal to b squared n. And this is always true for an ideal polymer chain. And it's going to be always true for this semester. Okay, things will start changing next semester in EMAC 352. And this is the result of taking whatever polymer we have, so polystyrene, polyethylene, polyethylene oxide, things like that, taking our polymer and constructing what we call a universal, sorry, not a universal, an equivalent freely jointed chain. Okay, so under the right conditions, regardless of what the chemistry is, we can construct an ideal polymer chain where the only things that we care about are the Kuhn length. And remember, that's just a measure essentially of the bond length in this equivalent freely jointed chain, and the number of Kuhn monomers that we have. Okay, so the very important things that we have, B, remember this is the Kuhn length. And this changes for every polymer that you have, okay? So it might be one thing for polystyrene, it's going to be a different thing for polyethylene, it's going to be a different thing for polymethyl methacrylate. And in general, we just look these things up. So for example, one common value that we use is that for polystyrene, the Kuhn length is 7 angstroms, or 0.7 nanometers. There's other ones. So I don't have a list with me right now, but polynipam is commonly used for thermoresponsive materials. People are looking at it for, for use in biomedical applications. Its Kuhn length is somewhere on the order of like 1 to 1.5 nanometers, okay? So like 10 to 15 angstroms. N, the number of Kuhn monomers, is going to be whatever your molecular weight is, so molecular weight of polystyrene, divided by the molar mass, or the molecular weight of the Kuhn monomer, okay? So this thing is actually the molar mass of the Kuhn monomer. So let me be a little bit specific in this. So for example, when we look at something like polystyrene, that's its chemical structure, and the molecular weight, or let's call it the molar mass to be a little bit more precise. The molar mass of styrene is about 104 grams per mole. All right. So if you were to take the molecular weight of your polymer and divide it by the molar mass of styrene, then that would tell you how many styrene monomers are in there. And in that case, you could calculate the mean squared end-to-end distance in that situation as C infinity times the number of styrene monomers that you have times the bond length squared. Okay, so this is using chemistry. The alternative approach is that we get rid of all the chemistry that we're talking about, and instead we know that the molar mass of styrene's Kuhn monomer, which might include many actual styrene monomers, but the molar mass of the Kuhn monomer M0 is about 720 grams per mole. So in other words, the Kuhn monomer in this equivalent freely joined chain is made up of something like 7 styrene monomers. All right. And so in that case, if we wanted to calculate the mean squared end-to-end distance, it would just be B squared times N. So the difference between these approaches is that when you're using the actual number of styrene monomers, you're going to have to look up C infinity. N is going to be the number of styrene monomers that make up your polymer chain. And L is the actual bond length in the backbone. So it's actually that. In contrast, when we have the equivalent freely joined chain, it looks something like this. And it has capital N Kuhn segments and a bond length, somewhere in here of B, or the Kuhn length. All right, so in the example above, little n is equal to the molecular weight of your polymer divided by little m0, right? Which in this example is 104 grams per mole. For using the equivalent freely joined chain, B squared, we have to look up the Kuhn length for styrene, or we'd have to measure it with some techniques that we'll talk about later. But we know that this is 7 angstroms. And in terms of N, the number of Kuhn monomers, it would be molecular weight of the polymer. Okay, so same molecular weight that I had up here, exact same molecular weight. But in this case, we would divide by the molar mass of the Kuhn monomer, right? Which in this example is at 720 grams per mole. So that's the difference, okay? That's how we get rid of the chemistry and extract the essential features of these molecules. Now, another thing that we could do, let me actually draw it above, let me pick a good color, above here. We could look at the average distance that each of these monomers is from the center of mass of the molecule, which is where I've placed that X. And in this case, we could calculate on average how big that is. And it might look something like that. And so in this case, this is denoting the radius of gyration. So again, it's the average distance of a monomer from the center of mass of the polymer. All right, so we could calculate that. So for example, if we wanted to actually derive a formula for the radius of gyration, which we won't do, but if we wanted to do that, we could calculate the center of mass position of the polymer chain. And we know that we have a certain number of monomers in there, right? We've got capital N Kuhn segments. And so we could calculate this by getting the average position of all of these things. And what I'm doing in writing this expression is I'm going to assume that all of the monomers have the same mass. And so if I did this, I would be summing up from J equals 1 to capital N. And I'm going to use the equivalent freely jointed chain in this case. And I would sum up the position of each of those monomers, so R sub J. Okay, and that would give me a vector that's telling me the position of the center of mass, like I've drawn up there. Okay, so that's the first step. And then the second step, I know that I would calculate RG squared, okay, because RG, the mean value of RG is going to be 0 for exactly the reason that the mean squared end-to-end distance is 0. Sorry, the mean end-to-end distance is 0. But I define this as the average, so 1 over n, of how far everybody is, so how far each monomer is, from the center of mass of the molecule. All right, and so what I do is I trace this through and I expand this, so I substitute, let me just outline this for you. I substitute this whole thing into there, and then I have all these indices and summations, and I have to manipulate the expressions quite a bit. And so the net result is that after much algebra, and that's all it is, it's just simple algebra, we get to a useful expression for the radius of gyration. So in this case, we can write it one of two ways. One way that we could write this is that RG squared, and I should say that the way I've written the expressions up here, this is only for a single polymer chain. And if you've done the HoloLens exercise already, or if you're about to, you'll see that this changes quite a bit. But for one polymer chain, the radius of gyration squared, after we do all of this work, all of this algebra, we get 1 over 2n squared, and we get these summations that come out. So I equals 1 to n, and the summation of j equals 1 to n of Ri minus Rj squared. Okay, so it becomes a lot of work to get to that expression. And then at the end of the day, the way that we calculate the radius of gyration of the polymers, we need to know the positions of each single monomer that's in there. Now that may seem like really silly, like how the hell are we going to know where all those monomers are? The answer is we don't, unless we're doing computer simulations. Okay, if we're doing computer simulations, certainly we know where all those coordinates are. But in general, we don't know that. So this expression, though, will allow us to essentially calculate what we expect the radius of gyration to be. And if we wanted to actually measure what it is, we don't know experimentally where all those monomers are. And so there's other techniques that we use. We use lasers or X-rays or neutrons to do that. Okay, so file that away back here. We're not going to deal with that right now. We're only going to deal with using this expression to calculate what the size of the polymer chain would be. So you can do a little bit more algebra, okay? So let's say a tiny bit of algebra. And if you care about this, if you'd like to see the algebra, then you could look on like page 60 of Rubinstein and Colby, one of the books in the syllabus, if you really want to see that, or I'm happy to go through it with you. But it's not too useful for calculating these things, okay? So after that tiny bit of algebra, we get an equivalent expression, Rg squared, which is 1 over n squared, summation I goes from 1 to n, summation j equals I, not j equals 1, to N, and you get the same thing, Ri minus Rj squared. So essentially, even though the radius of gyration is telling you the average distance of a certain monomer from the center of mass of the molecule, when you're calculating it, what you're really doing is you're looking at how far each monomer is from every other monomer in the polymer chain. That's the calculation you're doing. All right, so just notice that there's a 2 up here. There's no 2 down there. There's a 1 there. And there's an I there. Okay, so just pick out the differences. In practice, I find that this expression is much easier to use because it's a much more efficient calculation, right? You're calculating fewer terms. Okay, so let's do an example. Okay, so the example I want to do, I might have to actually type this in on my computer as I do it, but the example I want to do is 1. What is the radius of gyration squared for an ideal freely jointed chain? If we do that correctly, then what we should end up with is, where to go? We should get this expression in the orange box if we do it correctly. So can we get this expression? We'd better. So that's the first one, and then we'll plug in some numbers for a polymer, and we'll just calculate what Rg is. All right. Okay, so to do this, the way that we do this is we have to convert some things. So the first thing is we will convert the summation as I goes from 1 to n. We'll convert that to an integral, 0 to n du. Okay, and we're going to do the same thing for the other summation. So we're going to convert separately the summation as j goes from I to n. We will convert that to an integral. So this will be the integral from u to n, and we'll call this dv. All right, so if we do that, what our expression for the radius of gyration looks like is the following. The average, and let's write this now, we're going to look at the average across all of the polymer chains, okay? So if we just did this right here, that would tell us the radius of gyration for one polymer chain, but we need to really do this for a large number of polymer chains to get the right answer. So we're going to look at the average. So the average radius of gyration squared is going to be 1 over n squared. That comes from up there. And then we've got the 2 integrals. So we have the integral from 0 to n. We have the integral from u to n. And we need to put in the expression, right? So you can see up here, we just have the distances between monomer I and monomer j. And so in terms of this expression with the integral, what we're going to get is the average distance between the position of monomer u minus the position of monomer v squared. We're putting those pointy brackets around to denote the average. And then we get dv du. And so we just have to do this integral to figure out what this should be. So the real problem then is, what on earth is this thing? And so this is the first or the second time I'm going to introduce something that's universal for polymers, okay? So there were 2 universal behaviors, or there are 2 universal behaviors of ideal polymers. So the first one has to do with their conformation. The first one, we saw that the mean squared end-to-end distance can always be cast in this form. You get a bond length squared multiplied by the number of monomers in the chain. So this is universal. The other universal behavior is that polymers are what we call self-similar. And we will discuss this a little bit in the second when we talk about fractal dimension. But what I mean is if they're self-similar, if I draw a polymer chain like this, and I want to calculate its end-to-end distance, like that, then I can do this pretty easily with these ideal chain models that we've seen so far, right? So the mean squared end-to-end distance, r squared, is going to be b squared multiplied by the number of monomers that I have. And so if this over here is monomer n, and this over here is monomer 0, then I get the number of monomers would be monomer n minus monomer 0. I realize this is kind of silly, but you get b squared n. Okay, no big shock there. Now the reason that I show you that is because when I say something is self-similar, then if I look at a small portion of the chain, like if I were to look in this region, oops, come back. Hold on. I want to move my circle. Work with me here. There we go. Okay, sorry. So if I want to calculate the end-to-end distance of this part of the polymer that's inside this region, then let's say that the monomer starts here. That's the start of the chain that enters that region, right? So this would be monomer U. And then the chain kind of traces around. Oops, I went the wrong way. Doesn't change it though, right? You trace this chain around and then it leaves over here at monomer V. And so you could calculate the end-to-end distance of the region in the chain that's in that small orange circle, right? So of a subsection of the chain. And what self-similarity means is that if you wanted to calculate, let's call this, let's see, little g. No, sorry. Let's call this, I want to use the same notation that we're going to use later on in the course. So let's call this little Greek letter psi, xi, whatever, okay? So if I wanted to calculate that size, then it would be still the Kuhn length and then multiplied by the number of monomers. Well, the number of monomers in this subregion is going to be V minus U. All right, so this means that the thing is self-similar. The statistics that we use to get information on the size of the chain at large length scales is the exact same as the statistics and approach we use to get the size of the chain at smaller length scales. So what does that have to do with the radius of gyration? Well, what this means is that the radius of gyration, in terms of this integral formulation, is 1 over n squared. The integral as u goes from 0 to n. The integral as v goes from u to n. This thing here, right, that I've got the brackets, this is just the mean squared distance between V and U, between monomer V and monomer U. And because they're self-similar, that means that that distance between them is exactly that. Okay, so my expression simplifies a little bit, and I get B squared. Let me just be a little neat here. We get B squared V minus U dV du. So this is pretty easy, right? We can calculate this. In fact, what we could do is we could take B squared out of the integral and we could put it there. And so all we have to do is do this integral. All right. So we could do this by substitution. We could let V prime equal V minus U. And we could let u prime be n minus u. And we could see what our integral becomes. Okay, so if we make that substitution, this integral becomes b squared over n squared. The integral, let's see, when u is equal to 0, sorry, let me be careful. So we get 0 to n, and we get 0 to n minus u of v prime dv prime du. And we do that integral, and so we get, let me check my notes, b squared over n squared, integral from 0 to n of n minus u squared divided by 2 du. Okay, and so we can do this integral, and what we end up with is then b squared over 2n squared n cubed over 3. And we can see what cancels, right? N squared canceled out there. We get 6 in the denominator, so we get b squared n divided by 6. I'll tell you right now, this is super important. This is one of those things that you should keep up here because you use it so much. And so to summarize this, if we have a linear chain, so a linear chain looks like this, right? It's just a straight line. Then r squared is b squared n. Rg squared is b squared n divided by 6, or 1/6 of r squared. And we could take the square root, right? So we could get the root mean squared. R squared to the 1/2 would be b root n. And the root mean squared radius of gyration would be b square root n by 6. Okay, so we could do this for other architectures too. So for example, we could look, instead of a linear polymer, we could look at a ring. Okay, so a cyclic polymer. People make these. I've studied this in my own group. You get that the mean squared radius of gyration for this thing is b squared n divided by 12. So in other words, when you make a cyclic polymer, if it's the same molecular weight as the linear polymer, so in other words, if these two things had the same molecular weight, then you could see that the ring would have a smaller radius of gyration, but the radius of gyration would also scale the same way with n, and we're going to talk about that in just a second, what scaling means. As another example, you could have something, a different polymer architecture. You could have a star polymer, and this is also something that my group works on. So you could have a polymer that looks like this with a certain number of arms. So this has F arms. In this case, F is equal to 4. And let's just say that it had the same molecular weight as what I just showed. Then you would find, if you went through a calculation of this, that Rg squared for the ideal star polymer would be n divided by F b squared divided by 6. Okay, so that's more or less the radius of gyration of one of these arms. okay? Because N divided by F is the degree of polymerization of just one arm. So that's what that gives you. B squared over 6, that looks the same. And then you get this other factor that comes about, 3 minus 2 divided by F. Okay, so again, it looks similar. The expression becomes a little more complicated, but you can notice again that it depends on N in the same way. So for all of these different architectures, what we can see is that the radius of gyration and the end-to-end distance, but let's just only focus on the radius of gyration. The radius of gyration squared is proportional to N, or the root mean squared is proportional to N to the 1/2 power. This is the kind of thing that my group worries so much about. What are these exponents? Because they tell you so much about how a material behaves. So we spend a lot of time measuring these and figuring out what they are. Okay, so that's the radius of gyration. You see, it's not too much more complicated than the mean squared end-to-end distance. But let me give you a quick example. Okay, so let's just try to calculate something. In fact, let's do a calculation that I did in my PhD for my thesis, like every day for 5.5 years, okay? So I was working with, in my research, gold nanorods. Sorry, that's not a very good gold nanorod. So I was working with gold that looked like this. And what you can do is you can react gold with a polymer that has a thiol group on the end, and what you produce is a gold nanorod where you form a gold sulfur bond, and then you have the chain coming off. Okay? So this is a very common thing to do. It's a very common way to functionalize noble metal nanoparticles like silver, gold, platinum, etc., with a polymer. And the polymer that I was working with was every polymer physicist's favorite polymer, polystyrene. And the molecular weights that I typically worked with were 20,000 grams per mole. Okay, so even after however many years, 15 years, 10, no, sorry, I got my PhD 10 years ago. After 10 years, I still remember what the molecular weight is of that polymer. Now the question is, okay, if that's what you have, then what is the root mean squared radius of gyration? And in our language in this class, usually we'll just write this as RG. And you and I, as polymer experts, will understand that I mean that this is what you would get if you averaged across millions of different polymer chains, right? Okay, so what is it? Well, this is a linear polymer. So Rg is B times the square root of N divided by 6. Okay, I already told you that for styrene, this is something that we can look up, and B is 7 angstroms. I also told you that the degree of polymerization, the number of Kuhn monomers, will be the molecular weight of the polymer divided by the molar mass of the Kuhn monomer. And I know that. I can just look that up. And so I looked that up, and this will be, in this case, 20,000 grams per mole divided by 720 grams per mole. So let me open my calculator, and let's see what this gives us. This is 20,000 divided by 720. This is about 28. So that's not the number of styrenes in the polymer chain. That is the number of Kuhn segments in the polymer chain. If we wanted to use the number of styrenes, we'd have to use C infinity, the characteristic ratio, the number of styrenes, and the actual carbon-carbon bond length. But we're not going to do that. Okay, so that means that Rg is equal to, let's do this in nanometers, so 0.7 nanometers times the square root 28 divided by 6. And let me open my calculator again. And so this comes out to be 0.7 times square root 28 divided by 6. This is 1.51 nanometers. Okay, so that's the radius of gyration of that polymer. All right, so we've done that. Next thing that we are going to do today, we're going to talk about scaling and what I mean when I say scaling. And we're going to talk about the fractal dimension next. That is, what is the dimensionality of a certain shape? Okay, so now we need to talk about scaling. And scaling is a very, very important concept. Let's use a different color. So scaling. Super important concept when we're trying to understand the way polymers behave. So let me introduce this topic by talking about something that we all know. So let's consider a sphere. Okay, so if we wanted to calculate the volume of this sphere, we could all do that right now, right? So if we wanted to calculate the volume, we would write this as 4/3 pi r cubed. Now, we could write a bunch of similar expressions, but we would use different terminology to do that. So, for example, I could look at the value of 4/3 pi. And what is 4/3 pi? Well, I think I know what it is, but let me make sure. Okay, so it's 4.1887 something, something, something. So that means that the volume we could write as being approximately equal to 4.2 times r cubed. So what we're saying here is that this is equal. This is approximately equal. What else could we write? We could write that the volume is proportional to r cubed. So what we've done by doing that is we've said that the volume is equal to r cubed apart from some kind of constant that goes in front of it. And so I don't expect this to be particularly new for you, right? You've done this kind of thing your entire life so far. Now, where scaling is a little bit different is we write that the volume scales as r cubed. So this is the terminology that we use in polymer physics. We don't usually say proportional to, we say that it scales as. So in this way, you could figure that, for example, if the radius went to 2 times itself, if you double the radius of something, then since the volume scales as r cubed, then you would expect that your volume would end up being 8 times as large. I don't like the way I wrote that. It'd be 8 times as large if you doubled the radius, right? Now, where this scaling is especially useful for us, and this is a common source of confusion for people, is that, okay, we see that the volume scales as r cubed for the sphere. This gets really confusing for people because we could write it a couple of different ways too. So it is true that volume scales as r cubed. Okay, and sometimes I might just say volume is r cubed because these prefactors that go up front, this 4/3 pi, while we know it for the volume of a sphere, for some of the polymers that we study, we don't know what these prefactors are. And so we just don't know, but we know that certain things scale as something. So we leave out all those numerical prefactors because they're not that important for us. So it's true that the volume scales as r cubed, and it's also true that volume is equal to 4/3 pi times diameter over 2 cubed, right? Because radius is just diameter over 2. So this comes out to be 4/24 pi d cubed, right? If I expand that, I think I did that right. Or in other words, the volume scales as diameter cubed. So we've got two expressions here that come about from the scaling. The volume either scales as r cubed, the volume scales as the diameter cubed, or actually, it does both. And so the importance of this is relating two quantities. So we're relating the volume to some length scale of the object. And I don't care if it's the radius and I don't care if it's the diameter, because those things only differ because of a numerical prefactor. So in other words, we would just pick one of these, whatever one made sense, and we would go from there. Now, what does this have to do with polymers? Well, in the terms of polymers, we write that r squared, again, I'm going to drop those brackets with the understanding between us that we realize that that means the average over a large number of polymer chains. But r squared is equal to b squared n, or the root mean squared is equal to b n to the 1/2 power. So a very common thing that we will do, and you'll see this if you go to any seminars from polymer physicists, is we'll take this and we'll write that essentially the root mean squared end-to-end distance, the size of the polymer chain, scales as n to the 1/2 power. Similarly, we could say that rg squared, again leaving off those brackets, is equal to b squared n divided by 6, or rg is equal to b times whatever, square root of n divided by 6. And we get the same type of scaling. The radius of gyration scales as n to the 1/2 power. Okay, so this is good because both the end-to-end distance and the radius of gyration are giving us some information about the size of an ideal polymer. And we see that in both cases, that size for the ideal polymer scales as n to the 1/2 power. Okay, so that's something that I always keep in mind. The size for an ideal polymer scales as n to the 1/2 power. But in general, and we will see this more next semester, but in general, the size of a polymer scales as n to some power nu. And we will use this a lot, but for now, you can just remember that this is going to be called the Flory exponent. All right. Now, why is this important? Because if I were to measure a polymer chain, and let's say I measure its size for many different molecular weights, if I found that nu is equal to 1/2, then there's a good chance my polymer is ideal. Okay, so this Flory exponent is very, very, very important. But we're not going to really mess with it that much until next semester. So that's what I mean by scaling. There's many different ways that we can relate two quantities, and the scaling approach, where we get rid of the numerical prefactors, is the way that we usually do it, especially when things start to get very complicated. Okay, so the last thing for this section is this quantity that we call the fractal dimension. And this is a very curious kind of quantity. But the way it goes is this. Let's say that you have an object with a mass. What you would like to know is, how does the mass scale with the size of the object? Okay, so now the way that this could go is this could be any number of things. You could have any number of exponents that go up here. So in general, we write that this mass scales as r to some power d, and d we call the fractal dimension. There are other ways to do it, but relating them this way seems to be one of the easiest ways to relate them. Okay, so where this came about historically is we could look at something like the island of Great Britain. And let's see if I can draw Great Britain for you. Remember, the country is the United Kingdom. The island that the United Kingdom is primarily on is called Great Britain. Okay, Great Britain is not the country. All right, so let's see. If I was to draw the island of Great Britain, it would look something like this. There's something over there, and something over there, and it goes up. Oop, I ran out of space. Bad planning. Let's try again. It goes over here, goes back, goes around, up, squiggles. Oh, we get up to Scotland up here somewhere, comes back down, over. Oh, there's Wales. Okay, there's Great Britain. What they did historically is they looked at how what the length of this coastline was and found that it scaled. So the total, I guess I should say, perimeter of the coastline scales as some power. I forget what it scales with now. But the point is that if you had something that was completely one-dimensional, then D would be equal to 1. It would be a one-dimensional object like a line. If you had something that was two-dimensional, like a sheet, and you wanted to see this area, D would be 2, because you have a 2D object. If you had something like a sphere, then we get D was equal to 3. And so what they found historically, you know, let me just write this down to be complete. This is a 3D object. This is a 2D object. This is a 1D object. What they found historically was that the coastlines of these countries were not one-dimensional. They're somewhere between 1 and 2 dimensions. So I think Great Britain, don't quote me on this number, but I think that it has a fractal dimension of like 1.35 or something like that. It's somewhere between 1 and 2 dimensions. It's got some roughness to it. If you were to look at South Africa, let me draw the country of South Africa. South Africa is kind of an easier one to draw. The country of South Africa kind of looks like this. You've got something like this, goes around, back, up, and there's a little hole that's carved out of the country. Actually, there's 2 holes that are carved out of the country. There's one over here too. But if you were to look at the dimensionality of the perimeter of the country of South Africa, you would find that D was 1.1. It's closer to 1 dimension than it is to 2 dimensions. That also means that it's a smoother coastline than something like Great Britain. You could look at other countries. You could look at Canada. You could look at Norway, Finland, countries like that. And they're all going to have different fractal dimensions that characterize the dimensionality of the object. Now, this is important for polymers because this tells us something about the way they behave, and this gives us a way to characterize them in very particular ways. So let's go back to the case of the sphere, and we want to calculate what its fractal dimension is. So we want to see, how is mass related to size? Well, if this is a solid object that has a uniform density, then we know that the mass density is going to be the mass divided by the volume. And so that means that the mass is equal to the density times the volume, or the mass scales with the volume. Okay? So kind of starting this calculation out, it means that for a 3D object, the mass scales as volume. But we already figured out how volume scales. We know that volume scales as r cubed. So mass scales as r cubed. Cool. What if we had a 2D object, like an infinitely thin piece of paper? Okay, so its thickness is like negligible. How would we figure out how the mass scales with R? Well, we could have like an areal density, right? We could have an areal density, which is the mass of the sheet of paper per unit area, which would mean that mass is equal to that areal density times the area, or mass scales with area. And so if we were to do this calculation, mass would scale as area. And let's just say we've got, a sheet of paper that's roughly R by R. It doesn't matter if they're equal or not, but let's just assume that they are, just to make this a little simpler. This would mean that mass would scale as R squared. And so the question is, if you had a polymer mass scales as R to the what? Well, how would we do that? We'd have to figure out what the mass of the polymer is. Well, the mass of the polymer, let me undo that. So if we wanted to do this, we would approach it in a different way. What's the mass of a polymer? It's going to be the mass of a monomer multiplied by the number of monomers that we have, right? So let's say that the total mass is going to be the mass of the Kuhn monomer multiplied by the total number of monomers that I have. And this scales as R to the something, right? But what is N? Well, N is the number of Kuhn monomers that we have. We can relate N to R though, right? Because we went through all of this work, so maybe over here separately, we know that R squared is equal to B squared N. So this means that N is equal to R squared over B squared. Okay, so this is mass scales as m0 times n, which scales as r to some power, and we're trying to figure out what that power is. We know that n is equal to r squared over b squared, so that means that mass scales as m0 over b squared r squared. That's the same as this one right here, right? It's just the size of the object. And we don't care about these prefactors, right? The point of scaling is that we get rid of those prefactors. And so in this case, what we end up with is that the mass of the polymer chain scales as r squared, so our fractal dimension is equal to 2. Does that mean that the polymer is a 2D object? No, it's a fractal object. It's self-similar and all of this stuff, and we'll talk about this a little bit more. But it behaves in terms of the mass, it behaves like a 2D object, okay? So if you double the size of your polymer chain, your mass goes up by a factor of 4. Did I do that right? Did I get that backwards? Yes. If you double the size of your polymer chain, then your mass goes up by a factor of 4. Okay, so that's what we mean by fractal dimension. Fractals have the property that they are self-similar. And so that's why above, when we were talking about the radius of gyration, we could calculate RG for the entire chain, and that will behave similarly to the RG of a smaller region. This big RG is going to be equal to b square root of n divided by 6. This smaller RG is going to be equal to b times the square root of the number of monomers in that circle that I drew divided by 6. And so this is, again, implying that they're self-similar, and that's a property that fractals have, right? Okay, so that's our introduction to scaling, the notation and what scaling means, and fractal dimensions. And so we only have one thing left to cover, and that is what is the free energy of an ideal polymer chain. All right, so let's do that next, and then we'll wrap up for today. So last thing, again, free energy of an ideal polymer chain. let's start with the Helmholtz free energy, which is U minus Ts. And remember, why is it U minus Ts? Because F is a Legendre transform of U, which is a function of entropy and volume, to F, which is a function of temperature and volume. Okay, and so that's why we subtract off the Ts. So what we need to figure out is, what is the entropy of an ideal polymer chain? Okay, so to do this, we'll have to rely on the fact that we can calculate the Boltzmann entropy for a polymer chain as Kb times the log of omega. So what I'd like to know is that if I have a polymer chain with a certain number of monomers n, how many microstates are there? So how many microstates does a polymer with size r and degree of polymerization n have? To do this, we need to make a connection to all of the random walk stuff that we already talked about. So if you're a little fuzzy on that, I encourage you to watch that video again, or at least the parts that have to deal with this. But remember, when we were looking at a random walk with a large number of steps, what we found was that the number of microstates, now let me be careful here. What we found was that the probability in one dimension of ending up at a position x after n steps, I hope you can see the connection now between the random walk and the polymer, was equal to the number of microstates for the polymer at position x having n states divided by the integral over all of the microstates. Okay, so again, to put words to this, this in the numerator is the number of ways you could end up at position x in capital N steps. And this is the total ways to take n steps. All right, and that gives you the probability of so many ways of getting to position x in n steps. And so if you divide that by the total number of ways that you can get to any position x in n steps, and that gives you a probability. So the trick that we're going to use to calculate the free energy of the polymer chain is to rely on the fact that the number of microstates for this random walk for position x in n steps is going to be the same thing as the probability function that we've already calculated for arriving at x in n steps, multiplied by this thing, the integral of the number of microstates for all positions x. Okay, so just, I know this looks a little weird right now, but I want to remind you this thing is just a number. Okay, so it's not that important. So if we want to calculate the free energy of the polymer chain, then we need to calculate the entropy. So S, so let me write this out. So the entropy of an ideal freely joined chain, we will use this property of the microstates and the probability functions to get that. So S for the ideal polymer chain will be Kb times the log of omega. And now we have an expression for omega, so this will be Kb times the logarithm of whatever probability function we're using. I'm just going to put in the 1D function right now. And that is what it is, right? We got the probability. Then we'll take the approach of splitting up this logarithm, right? If you have the logarithm of the product of two numbers, and that becomes the sum of two logarithms. So this is going to be the same thing as KB times the logarithm of that probability function plus KB times the logarithm of whatever this thing is. It looks ugly and like it'll be a real pain for us, but it's actually not that bad because it's just going to be a number and it's going to be grouped in with some constant. Okay, in fact, what we could do is let's put in the probability function, okay? So in one dimension for a large number of steps, that probability function, P1D, let me change the terminology here. We'll call this R, call this capital R in N. So in one dimension, the probability of ending up at position R after N steps is going to be that thing that we already calculated, right? We get square root of, let me make sure I get this right. Well, I'll give you what it is because there's going to be some changes from what we talked about last time because we're talking about a polymer now and not a person walking down the alleyway. So what this ends up being is the square root of 3 divided by 2 pi n b squared, and those are the same parameters from the ideal polymer chain, and then multiplied by the exponential of minus 3r squared over 2nb squared. So this is the conversion from that probability that I showed you for the random walk to what it is for the polymer chain. Okay, so this is in one dimension. In 3 dimensions, which is the case we care about, we multiply all these one-dimensional functions together, and we end up with something that looks like the probability in 3D for R and N is going to have a different coefficient out front, and there'll be a homework problem where you get to play around with these. These are just to normalize the probability distribution. But it comes out to be 3 over 2 pi nb squared to the 3/2 power, and then the same looking term, right? So the exponential of minus 3r squared over 2nb squared. If that's kind of confusing, you can think about this as r in the x direction, whereas this r for the 3D case is the r in all directions. Let me draw that to show you what I mean. So if I was to draw a single polymer chain in X, Y, and Z, one single conformation of it, and the way that it will look in the HoloLens if you haven't seen it yet, is a polymer chain could be all over the place, right? And so let's say that over here is where the polymer chain starts. And there's where the polymer chain ends. And so what the probability function is saying is that if I start right there at that green bead, what is the probability that after n steps, I end up in that white box? So what is the probability that after n steps, I end up over there where this is R? Okay, I hope that makes sense. That's what the probability function is telling us. And I hope that you can see the connection between that kind of probability function and what we did with the random walk, right? Because this yellow polymer chain is a random walk in space because the bond angles can be anything, right? So it's flopping around all over the place. It's weaving its way through space randomly. And so this function that I just drew is telling us exactly the probability that we'll end up right there after n, capital N steps. And that will be accompanied by being a distance, a certain distance r from where you started. Okay, so if that's the case, then now we can start to split this up and figure out what is going on in terms of our entropy and then our free energy. Okay, so the entropy we will calculate in a way similar to this, except we'll use the three-dimensional function. So in 3 dimensions, the entropy of a polymer chain that has a size r and a degree of polymerization n is going to be Kb times the logarithm of that 3D probability plus Kb times the logarithm of the integral of the number of microstates. Let's use consistent notation, so say r and n dr. Okay, so this thing here, if you notice, we're integrating out the r, so it's not going to depend on r. So this is kind of like, well, first of all, it is a constant. This is the entropy of a polymer chain that has 0 size and n monomers. It's kind of like the base entropy, is one way to think about it. So that means that our total entropy will be Kb times the log of that probability distribution, and then plus S of 0 and n. And just to say it one last time, this is a constant. It doesn't depend on the size of your chain, at least the size r of your chain, right? It certainly depends on the number of monomers you have, but that's it. Okay. So let's put in our probability distribution. We're going to get, this is equal to Kb times the logarithm of 3 over 2 pi nb squared to 3/2 exponential of minus 3r squared 2nb squared plus S of 0 and n. And again, we've got this logarithm. We have a product of 2 terms. We've got that term. We have that term. So this one can just come out as the logarithm of some constant, and we can group it in with that one, right? Because we don't really care what that is. So this comes out to be Kb logarithm of the exponential of minus 3r squared 2nb squared plus S of 0 and n. So we took this term and we brought it down into that. And the logarithm of an exponential, that's easy. So this comes out to be Kb times minus 3r squared over 2nb squared plus S of 0 and n. So that's the entropy of an ideal polymer chain. We usually write it a little bit differently. We usually write it minus 3/2 Kb r squared over nb squared plus S of 0 and n. Okay, so just a couple things to note about this equation. Hopefully you can see how it comes about. It's not that hard to derive, but it's a comparison of the size of your polymer chain to what it should be. Okay, so in the numerator is the actual size of your polymer chain. So this is, for example, the entropy of a polymer chain that has a size r and a degree of polymerization n. It's equal to minus 3/2 Kb times the actual size of the chain relative to the ideal mean squared end-to-end distance, right? So that's our entropy. Very important. Let's draw a box around this so we don't lose it. So we've got that. And now that we have the entropy of our polymer chain, we just need the free energy, right? So the free energy of our polymer chain that has a size R and N is going to be U. So U of whatever, R and N, minus T S of R and N. All right, so we're going to get, let's see here, U of R and N minus T times S. So we've got T times minus 3/2 KB R squared and B squared plus TS of 0 and N. Okay, that looks all right. And so we're going to group these things together. We're going to assume this is independent of R. In other words, the internal energy of the polymer chain doesn't depend on its size. It only depends on the number of monomers and how much they're jiggling around, right? So we get like U would be F over 2 kBt per monomer, but that doesn't depend on the size, right? So we don't really care how big the polymer chain is. It doesn't matter. Point being, we're going to group this term, Ts of n and 0, with this term. And so our free energy is going to look like T, well, let's write it in a different order. We'll have kBt, sorry, 3/2 kBt. I like to keep the kBt's together. Times R squared over N B squared. And then the rest of those terms that don't depend on the size of the chain will just be some free energy of just having those N monomers there. So this is the free energy of our polymer chain. And I'm going to leave it there for today, okay? So this is the key result from this last part of the video, is that we get the free energy of the polymer chain. It only depends on the size of the chain and the number of monomers. We've got this constant term that we'll deal with later. And that's it. And it depends on the size of the chain with respect to what it should be. Okay, what our theory tells us that it should be. So the larger your chain becomes, the more the free energy increases. Okay, and vice versa. Okay, so that's the free energy of the polymer chain. This is the free energy of a freely jointed chain. And that's all I have to say about it. What we'll do next is we'll use this in the next class or two to figure out why rubber bands and other polymer networks behave the way that they do, what their modulus is, how to improve the strength of a material. And you'll see really that the strength of a material like a rubber band or something like that, at the end of the day, it all comes down to what its free energy is, which at the end of the day all comes down to the probability that it has a certain size, which all comes down to the number of microstates and the number of ways that you can rearrange the polymer chain. Okay, so that's kind of going from our key result here of the free energy all the way back to counting microstates and making that connection. So what we're going to do in the next class or two is we're going to use this connection between the microstates, the free energy, and the fact that this polymer chain is ideal to figure out why the mechanical properties of a material are what they are.